Hey guys, Mr. Kennedy again. We are going to pick up where we left off with Chapter 1. This is your Chapter 1 Intro to Environmental Science lecture video number 2, so part 2. Here we're going to start looking at what is a resource and some of the pressures that are put on our natural resources by us humans, people, and what we can do about that, okay, in the long term. Okay, so first thing I have for you here is basically just the definition of a resource. A resource is anything that we get from our environment to meet our needs, and I've got a list here around that little blue marble that we get to share called Earth. That is not an exhaustive list. There are lots of other things that could qualify as resources, but that's just meant to kind of give you an idea. So our resources fall into two categories. Natural resources, again, are things that are vital to our survival. The two big categories that we like to talk about in terms of natural resources are renewable resources and non-renewable resources. There are some resources that are outside those two categories. They're called perpetually available resources. Sunlight, wind, wave energy, stuff like that fall into those categories. No matter how much you use sunlight, unless the sun somehow burns out, like you're not going to use it all up, okay? Same thing with wind and stuff like that. Renewable, non-renewable resources, a little bit different scenario there, okay? To be renewable, I always say you have to be renewable over short periods of time. And by short, I'm talking about things like your lifetime. So timber, water, soil, wildlife, things that can be destroyed and or things that can be replenished within your lifetime are considered renewable resources, right? We could destroy the forests. So that's a renewable resource. We can also replace a forest or replenish a forest within your lifetime. So it's renewable. Non-renewable resources, kind of flip the script there. These are things that are not replenishable or not replaceable. So when you think about a non-renewable resource, it's oil, coal, minerals like that from the planet that once you use them, they're gone. Now, I have had students argue in the past, but Mr. Kennedy, like you can, make coal. The reality of it is oil and coal, yes, plants and animals are still dying and maybe still being compressed in rock strata, but they will not form coal and oil within your lifetime. So for lack of a better way to put it, we just say that those are non-renewable resources, regardless of the fact that, yeah, dead plants might become coal in, I don't know, 100,000 years, all right? Another little slightly different way to look at it is this chart. Again, this is kind of like our resource, map in total. You've got your solar capital, which is basically that which comes from the sun or the energy that comes from the sun. The sun produces or provides 99% of the energy, that we use here on Earth. And then your earth capital, that's where all of your other resources go. Whether they're renewable or non-renewable. If it comes from the planet itself, it's considered earth capital, not solar capital. Now, to give you one last little piece of perspective on this idea of renewable versus non-renewable, I threw this table together for you here. Not really, so that you could, again, memorize the definitions. But I want you to look underneath those red and green columns and look at the percentages that I've given to you there. So on the green side, we've got renewable resources, biomass, hydropower, geothermal, wind, and solar. And on the red side, we've got the non-renewable stuff, petroleum, natural gas, coal, uranium, and the like, okay? Now, again, these are important to know as examples of renewable and non-renewable, but what's even more important than that is look at the percentages of our use with regard to how we live, okay? So on the renewable side, we, in terms of energy, only get about 3% of our energy from biomass. Again, roughly 3% from hydropower, way less than that from geothermal, wind, and solar. On the non-renewable side, those numbers are crazy big. Petroleum, 38%, natural gas, 23%, coal, 23%, and then you've got nuclear and propane down there at the bottom. If you add all of those things up, about 6% of our global energy supply is met right now by a renewable resource, and the rest of it is non-renewable. Okay, that's scary, because basically what that means is if we keep on the path that we're on, I don't know if it's this generation, next generation, or 10 generations from now, but the point is, we will run out of petroleum. We will run out of natural gas. We will run out of coal because they're non-renewable resources. And that seems to be our favorite thing to use for energy right now. Okay, so if maybe we switched to the green side, we wouldn't have to worry so much about where our energy is going to come from on a day-to-day basis, or even for future generations, because those resources are not exhaustible. Okay, and there are countries that have gone, and made the shift. You take a country like Iceland as a big fat, for instance. They have 100% of their power needs met by hydropower and geothermal. Now, they do have some unique geography and where they're located, so they can take advantage of something like geothermal much more easily than we can, say, here in Fresno. But it's just a case in point where there are some countries that are making the switch. The U.S. is just not there yet, for reasons that we'll talk about as we get deeper into the course. Another thing to think about in terms of resources is our biodiversity. Biodiversity is a measure of the different life forms on Earth, and it is a potentially renewable resource as long as we don't use the life forms faster than they can reproduce. When you think about biodiversity and its importance, yeah, there's an aesthetic thing to being able to look out the window and see a variety of trees or a variety of different animals or whatever. But realistically, the biodiversity on this planet provides us with our food. When you talk about what you eat on a daily basis, it comes from other living things. As you eliminate biodiversity, you eliminate a potential food source. Another thing that biodiversity is important for is medicine. There are countless medicines that come from other living things. As you eliminate biodiversity on this planet, then you also eliminate the potential resource of medicine and medicine discovery, right? So that's why biodiversity is really, really important and should be protected and considered in how we interact with the environment. Remember the Jenga game, right? So if we pull blocks out, we lose a species, like there's no way to replace it. So the key to biodiversity is to use it responsibly, and to not eliminate organisms or use organisms faster than they can potentially reproduce. Because we all know that no matter what we do, we still need to eat. Okay, so being an environmental scientist, it doesn't matter if you're a vegetarian or an omnivore. Everybody has like their favorite food, right? So the key is, if you're a vegetarian, whatever your favorite food is, if it's soy or whatever, or if you're a carnivore and you really like cheeseburgers, okay, like the idea is you don't eat cattle faster than cattle can be replenished, or you don't eat plant material, soy, faster than soy can be replenished. The key is you don't have to stop eating what you're eating, right? You just have to not use it faster than it's being replenished, okay? Here's a case in point in terms of the forest. Forest is a plant, so it's biodiversity. It's potentially a renewable resource if we use it responsibly. Sometimes people think that because I'm an environmental scientist, I might come out and say, hey, like you can't cut down any trees. Believe me, I'll be the first one to tell you that I appreciate paper products, as long as they're done or used responsibly. Like I'll use a paper towel, right? I'll use a paper plate, but those things are recycled or composted. Okay, so that's used responsibly. That's the key, right? You use the things responsibly and recycle and compost as much as you can. You have to have paper, for school. You have to have, toilet paper, right? So you have to have paper products. So how do we extract that from the forest in a renewable way? Well, this is an example. You want to go in and do what's called selective logging as opposed to clear cutting. Selective logging cuts just specific patches of trees out here and there without destroying the forest. That protects the other wildlife in the area, still gives them a place to live, reduces your environmental impact in terms of erosion, and still makes it possible for those trees to repopulate the area. Clear cutting, as you can see there, you just go through and you wipe out everything. There's no way, there is no way that these trees are going to recover here in this space. Okay. Unfortunately, I did a little travel over the past couple of summers, and there are still places, even here in the United States, that practice clear cutting, right? They just basically mow the forest down. If we live by what you see there on the right, then the forest is no longer a renewable resource, right? It would be a non-renewable resource because once the trees are gone, they're gone. Okay, here's a couple of other examples. This is what's called the tragedy of the commons. So the tragedy of the commons is something that you're going to do a little experiment with later in the week. And it's really centered around this idea of using our resources, but in a sustainable manner. A commons is a common property or resource, basically that is available to everybody free of charge. So in this case, you see these codfish and a graph from the Georges Bank where the codfish are caught. So the codfish, obviously lives in the ocean, and the big question is, who owns the ocean? Who can tell you how many fish you can possibly catch, right? There are countries like the United States that does impose fishing limits. We'll get to that later. But outside of that idea, if I'm from another country that doesn't impose fishing limits, that's where we start to have problems with these commons. Humans by nature are fueled by materialistic things more often than not. And what that means is basically money. Okay. So if I go out in the Georges Bank and I catch lots of fish, then I can sell those fish and ultimately make lots and lots of money. And that's what is at the heart of the tragedy of the commons. If you have boat A and boat B out at sea catching lots and lots of fish, whoever catches the most fish basically makes the most money, right? So do you see the problem? Do you see the drive? If I want to make lots of money, I need to catch lots and lots of fish. And if we operate with that mindset of it's all about me and it's all about right now, and all I need to do is like line my pocketbook, fill my bank account, then you're going to go out there and you're going to try to catch as many fish as you possibly can. Okay. If I'm boat B and I don't catch as much fish as boat A, I run the risk of going out of business, which means I can't feed my family, I can't pay my mortgage, right? So there's the competition, right? And there's the fight for that resource. People of the world, as I said a while ago in the previous lecture, they all want what we want. And that means they want a home, they want luxuries like what we have, and that creates this competition for these resources. So, the problem that we run into here is directly related to that materialism. So if we go out and we catch, tens of thousands of pounds of fish without really thinking about the future, what we run the risk of is catching more fish or fish faster than the fish can replace through reproduction. If I've got 100 fish, right, and I catch 99 of those fish in a pond or out at sea, that leaves one fish to try to repopulate the pond the next year, right? Assuming that fish is pregnant and has already laid eggs and those eggs are fertile or whatever, that one fish might only be able to add a second fish to the population. So now a pond in a year, instead of having 100 fish, is going to have 2 fish, right? So what am I going to do? Oh, if I catch the most fish, I make the most money. So I'm going to go out and I'm going to catch those 2 fish. Uh-oh. Well, what do I do in the next year? I didn't leave any fish behind, right? There's no fish for reproduction, and now everybody's out of business. That's the tragedy of the commons, okay? And it comes from that selfish greed and that short-sighted nature, all right? So that leads us to this idea of sustainability. If we want our resources to last for the long term, we need to use them at what is referred to as a sustainable level. A sustainable use of resources satisfies our needs without jeopardizing our earth capital or the needs of future generations. Okay, so a sustainable system is one with long-term survivability and functionality. Right. Now, this concept of sustainability was written about in a text by Brundtland in 1987. And basically, the point of that article was just how do we meet the needs of the present without compromising the ability of the future generations to meet their own needs? Okay. What that really requires of us is to change our perspective on our resources and how we're going to use those resources, right? We need to look at our resources as things that benefit and must be available to all humans from this generation forward, not just this generation and done, right? So economic growth alone can't be enough. Political stability, democracy, equitable economic distribution, all are needed to ensure that we have the resources, not just for you right now, but for your kids, your kids' kids, and so on for generations to come, right? Many ecologists view our world population, our continued growth, really as impossible to maintain in the long run due to the limits that are imposed by non-renewable resources. So basically what that means is we've got 7 billion people on Earth. Our global population is growing at about 1.3, 1.5% right now. Our global population, and I've got a statistic on this later for you, will double in about 50 years. So if we've got 7 billion people on Earth, we're going to have 14 billion people on Earth in about 50 years. So what ecologists are saying is like, guys, we can't sustain like that kind of growth with the behaviors that we have right now in terms of our utilization of resources. You might remember from biology the concept of exponential growth followed by carrying capacity. Eventually, all populations will have to deal with that idea of carrying capacity if they don't utilize their resources in a sustainable way. Unfortunately, we are the only species on the planet that has the brain power in order to like recognize what we're doing. Lower species, they don't have that ability. If it's springtime and the flowers are blooming and that flower is your food source, you just eat, right? You don't go, well, I'm going to eat 2 flowers and I'm going to save 2 flowers for next time, right? You just eat, okay? Humans are the only ones that have that cognitive ability, so that gives us that responsibility. Here's a couple more graphs and examples, okay? This goes back to those fish, the codfish in the Georges Bank. So the idea is we can use those fish as a resource as long as we do not deplete the population of fish below, right, these soft limit depleted ranges. If you just kind of sum that up in plain English, what that means is we're never as an environmental scientist going to go out and say, hey, stop eating codfish, period. Hands down, you got to find something else. That's not our job. Environmental scientists are going to go out there and they're going to say, look, you need to use this fish responsibly, which basically means you got to set a limit on how many fish you catch each year, right? And then don't exceed that limit. Because if you do exceed that limit, you're going to get to this spot where your Jenga tower will fall. Okay, that's our job. It's a difficult thing, you know, to conceptualize and deal with as a human because, again, we are heavily invested in materialism and financial gain. But you can see what's happened to the cod harvest in the North Atlantic as a result of not heeding those warnings from environmental scientists. If you go back into the 60s, I mean, hey, you could catch tons and tons of fish and it was not a problem. But if you go here to the 2000s, there's hardly any fish left. And if you kind of look at like who's to blame, this graph is a graph of non-Canadian catches versus Canadian catches, right? Because the Canadians do a lot of cod fishing. So the Canadians were limiting the number of fish that they would catch to try to maintain some sustainability of the fishery. But the non-Canadian countries in the area were not. Look what happened in 1968, okay? The non-Canadian catch is like, 10 times greater than the Canadian catch. That's not because Canadians are poor fishermen. It's because they realized that they needed to limit how many fish they catch in order for there to be fish in the future. As a result, right, look what happened in the future. Canadians started catching more fish and they started sanctioning the non-Canadian fishermen. And by the time we get to the 2000s, it's a lose-lose for both. Okay, there's no fish left. Realistically, this resource use is driven by human population growth. The more people that we have on the earth, the more pressure there's going to be on our resources. Again, right now we're at about 7 billion people on earth, and that number is only growing. Okay, as you think about our growth is currently in what's called an exponential phase of growth, which means that it's growing faster and faster over shorter and shorter time periods. Okay, this graph is meant to kind of give you an idea of the difference between the exponential growth and the linear growth. Okay, so exponential growth is growth that occurs faster and faster over shorter and shorter time periods, and linear growth is growth that is the same no matter what. In terms of its growth, it'd be kind of like a job where you get a $1 raise per year. Okay, this type of growth was first explained by Thomas Malthus. He's the guy that helped Charles Darwin with his theory of evolution by natural selection. And Malthus basically said that populations tend to grow at a rate faster than what the environment can support, right? Those that really buy into Malthus's ideas are called neo-Malthusians. And basically their theory is that we will eventually hit carrying capacity. Our population will get so big that we will have outstripped our agricultural land's ability to provide food, and we'll be facing stuff like starvation and war and disease. The one thing that's our saving grace right now is agricultural advances. So due to agricultural advances, we're holding off this carrying capacity, and still we're able to feed people without starvation, war, disease, and all of that. But as our population grows, like it's kind of a shell game. It's, you know, we got to make another advance to keep feeding people, while at the same time people are demanding houses and entertainment and roads and malls and all that. So we're losing agricultural land. So we're having to feed more and more people on less and less space, right? Which is a problem that we're going to have to deal with. Okay. All right, so I'm going to stop there, and in part 3, the last installment of chapter 1, we're going to talk about the growth of these populations and how we calculate that, and ultimately where the hope is for the future. All right, so I will see you in part 3.